per unit system applied to ideal single-phase transformers. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to discuss with you the per unit system applied to ideal single-phase transformers. And to do so, I'm bringing this exercise. I am going to read the exercise for our debate. Per unit system applied to ideal single-phase transformers. A simple power system is shown in the figure. This system contains a 480 volts generator connected to an ideal 1 to 10 step-up transformer, a transmission line, an ideal 20 to 1 step-down transformer, and a load. The impedance of the transmission line is 20 plus J60 ohms, and the impedance of the load is 10 phase 30 ohms. The base values for this system are chosen to be 480 volts and 10 kVA as the generator. Letter A, find the base voltage, current, impedance, and apparent power at every point in the power system. Letter B, convert the system to its per unit equivalent circuit. Letter C, find the power supplied to the load. And letter D, find the power lost in the transmission line. Okay, my friends, the first step of the solution is to establish the base values for each region. Region 1, the generator side. Region 2, the transmission line side. And region 3, the load side. Let's begin with region 1, the generator side. The solution for region 1. The base value of the voltage I'm calling it VB1 because we're talking about region 1. As the exercise said, is (480 volts). The base value for the apparent power for region 1, as the very exercise said, as B1 is equal to 10 kVA Now we need to find the base value for the impedance, ZB1. And how are we going to calculate this value? We're going to use this expression VB1 squared divided by SB1 using this expression and the values given by the problem, we find that it is 23.04 ohms. Okay, these are the base values for region 1. Now, let's do the same for region 2. For region 2, we need to pay attention on the turns ratio of transformer 1. Okay? The turns ratio A is equal to 1 over 10. Then the base value of voltage VB2 is going to be equal to I'm going to explain it first before using the numbers. It's going to be the base value of region 1 divided by the turns ratio. Okay? Since the base value of voltage for region 1 is 480 volts, and the turns ratio 0.1, we find that VB2 is equal to 4,800 volts. Again, we are going to use SB2 as 10 kVA. Subsequently, we have to find for region 2 the base value for the impedance, and it's going to be ZB2 equal to VB2 squared divided by SB2. We simply use the values, this squared divided by this, and we find 2,304 ohms. Okay? These are the base values for region 2. To finish letter A, we need to find the base values for region 3. And again, we are going to consider the turns ratio of the transformer. The turns ratio of this transformer is A equal to 20. Then, for region 3, VB will be equal to VB2 divided by the turns ratio. VB2 is 4,800 volts, and the turns ratio 20, and we find 240 volts. as it was done for the other regions, the base value for the apparent power is equal to 10 kVA. And the impedance, again, is going to be VB3 squared divided by SB3. We are going to use this value, 204 volts squared, divided by 10 kVA. And we find 5.76 ohms. This is all for letter A. Now for letter B, what does letter B want? Letter B wants us to convert the system to its per unit equivalent circuit. Then we erase here. No, I'm not going to erase. I'm going to redraw it below here. It's going to be like this. Okay? Now, the voltage of the generator is written in per unit, the impedance of the line is written in per unit, and the impedance of the load is written in per unit. And we've gotten rid of the transformers. In the per unit circuit, the transformers don't participate. Transformers don't participate in the per unit circuit. Then a current is going to flow here. First of all, let's calculate these values in per unit using the base values that we found for each of the regions. The voltage of the generator in per unit is going to be 480 volts, 0 degrees, divided by which is equal to 1 phase 0 degrees per unit. Here it is in volts. Here it is in per unit. Now the impedance of the line will be equal to this value here, 20 plus J60, divided by the base value for the impedance of region 2, which is 2304 and then we find 0.0087 plus J, 0.026 per unit. This value here is in ohms. This value here is in per unit. And in a similar way, we are going to find the per unit value of the load. The per unit value of the load is this value here, the actual value, divided by the base value for region 3, which is and then we find (1.736 phase 30 per unit). Observe that in the original system, IG is different than I line, and they are different than I load. However, in the per unit system, only one current flows from generation to consumption, to generator, from generator to load. Now we are going to find this current here. The value of the current is the division between the voltage of the generator in per unit and the sum of the impedances okay? The division between the voltage and the impedances. And if we use the values that I showed you, we find the value for the current as (0.569 in the phase -30.6 degrees per unit. This is not in amperes, this is in per unit. Now we are going to calculate the real power delivered to the load. We are going to use this current here, the real power delivered to the load in per unit. Is equal to the absolute value of the current squared times the real part of the load, which is the resistance. And then, if we convert this polar form into the Cartesian form, we're going to get the real and the imaginary part. We are going to use the real part here and multiply by the magnitude of the current squared. And then we find 487 per unit. To convert again from per unit to the actual value of the power in watts, we need to use the base value for region 3. And how do we do it? I'm going to show you. P load will be equal to P load per unit times the base value for region 3. And if we use the base values that I showed you on the board, we are going to find approximately 4.9 kilowatts. In a similar process, we are going to find the power lost in transmission. The power lost in transmission is going to be the power of the line in per unit, which is the current, the magnitude of the current squared times the resistance of the line in per unit. If we use these values that I showed you before, we're going to find .00282 PU. This is in per unit. To convert it into watts, we need to use the apparent power for region 3, the base value for region 3. And then P line is going to be if we use this value here, and the base value for the apparent power of region 2, we find 28.2 watts. Okay, my friends, this was the exercise that I wanted to show you. I hope you liked it and enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!